In this blog post, we will continue discussing about the periodic properties. At this point, we have already talked about the covalent radius, which is basically the atomic radius, and the ionic radii. Okay. Today, it's more about the ionization energy, or the tendency to lose electrons, the electron affinity, which is the opposite, is the tendency to gain electrons, and the metallic character that it's pretty much related to these other two. So to continue with this, and just as a refresher, this is the periodic table, and it's just the periodic properties, and learning about the periodic properties is just about understanding how these periodic properties change as you move through the periodic table. So the first thing that you have to remember is that if you go left to right, the first thing that you have to keep in mind is the effective nuclear charge, because the effective nuclear charge has a big impact on all periodic properties. So in this case, if you go left to right in the periodic table, the effective nuclear charge will increase. And what does that mean that the effective nuclear charge increases? Then what it means is the nucleus is stronger. Think in terms of the charge. This relates to the charge of the nucleus. Is stronger means the charge of the nucleus is stronger. So if the charge of the nucleus is stronger, then the electrons are more attracted to the nucleus. Okay, and that has an impact. So increasing that effective nuclear charge, the electrons being more attracted, they want to be closer to the nucleus than the atomic radii decreases. The atom gets smaller. Okay, if the electrons want to be closer to the nucleus, then the atom gets smaller. Now that's the first thing. Now the effective nuclear charge, if you go down the group, then the effective nuclear charge pretty much remains constant. Okay, but the effective nuclear charge has less of an impact as you move down the group, because if you go down the group, basically what is happening is you are adding layers of electrons, and those electrons are farther away from the nucleus, and the result is the atom gets larger. Okay, so these are the principal outcomes that you have when you look at the effective nuclear charge and how it impacts the size of the atom. And as you move down the group, you're basically increasing the number of layers of electrons. So those are the main impacts on the size of the atom. Now, the size of the atom has an important consequence when it comes to ionization energy. So the next periodic property is ionization energy. And ionization energy is basically how much energy you have to provide to remove an electron from an atom. Okay, it's always a requirement, energy required. So that means the ionization energy is always positive. You have to provide energy to remove that electron, and it's related to a particular reaction. The reaction is you have your atom in the gas phase. This is very important. You have the atom in the gas phase, and then you are removing. You can say removing or losing. Okay, and if you remember a little bit from last semester, then it represents sort of an oxidation. Okay, you are removing an electron. That's the important thing. You are doing this reaction in the gas phase. So it's not your normal oxidation. You are required to have the atom in the gas phase. Now, if you have the neutral atom in the gas phase, and you're removing just one electron, then that is the first ionization energy. And the first ionization energy we represent it as IE1. You're removing the first electron out of that atom. Now you can keep removing electrons from the atom, correct? So the second electron that you're removing, now you are removing that second electron from the what you were left with after removing the first one. So this is the +1 ion. The second electron, you are actually removing it from the +1 ion. So the second ionization energy is your +1 ion in the gas phase, and that one is losing an electron and is forming a 2+ ion, also in the gas phase. Okay, and if you're removing a third one, then you are removing it from the 2+ ion. Okay, so that's the sequence. It's not, if you refer to the second ionization energy, no, you are not removing two electrons at the same time. The ionization energy, you are always removing one electron at a time. You start with the neutral atom, and then you produce the +1 cation. The second electron comes from the +1 cation. The third electron comes from the 2+ cation. Okay? So the training ionization energy is that, again, you have to understand how the ionization energy changes from as you move from the periodic table. So here we have different values for that, and let's focus here on the first two. We have hydrogen and helium. So hydrogen is here, helium is there, and then you are moving left to right, and the ionization energy is increasing. Okay, it's increasing in that left to right. Let's do it. Let's write it like this: left to right, ionization energy increases. Generally speaking, you will see that every single time. Lithium is here, and then you go all the way to neon is there. You are moving also left to right, and what you see there is that the ionization energy is increasing. Now you look here, hydrogen, lithium is down there, then sodium, which is here, and potassium, which is there. And what you see there is that it dramatically goes down from hydrogen to lithium, but then as you move down the group, okay, the ionization energy is decreasing. Okay, so those are the things that you have to remember. Left to right, generally speaking, the ionization energy increases, and get down the group, the ionization energy also, sorry, not also, down the group, the ionization energy will decrease. Now, what is the relationship with effective nuclear charge or atomic size? So it's easier to see it from the point of view of atomic size, because if you have that the size decreases, so to speak, which is what happens as you move left to right, then what you see is that ionization energy is increasing. And if the atom gets smaller, then the electrons are closer to the nucleus. So if they are closer to the nucleus, they are more attracted to the nucleus, and therefore that's why it's harder to remove from the atom. Now, as you move down the group, what happens with size? Size increases. Those electrons are farther and farther away from the nucleus. Because they are farther away from the nucleus, they are less attracted by the nucleus, so they become more easy. It's easier to remove them from the atom. Okay, so that's what you observe here. Generally, it will increase in any given period. Generally speaking, the ionization energy increases. But if you move down the group, and you see that in the halogen groups as well, the ionization energy will decrease as you move down the group. Okay, so remember, across a period, okay, this is left to right. Okay, the ionization energy increases. It refers to the first ionization energy, but for anyone, it's going to be practically the same. Left to right, the ionization energy increases. Down a group, okay, down the group, the ionization energy decreases. The atom is larger. okay, and left to right, the atom is smaller. Okay, you can always use that comparison. So ionization energy and atomic size, atomic radius are hand in hand. They go in opposite directions, but they are hand in hand. It's easy to relate ionization energy with the size of the atom. Now, electron affinity is the opposite of the ionization energy. There is an energy associated with gaining an electron, and the reaction is this. And I forgot to say that with the ionization energy reaction, but these two reactions, the ionization energy and the electron affinity, those are two reactions that you have to memorize, because you might be asked, okay, if you have several options here, which one represents the ionization energy, or the second ionization energy, or which one represents electron affinity? So you need to make sure you know the difference between those two. However, here for electron affinity, the substrate is the same. You always start with the neutral atom. Okay, and probably with electron affinity, it's the same process in terms of, for example, the electron affinity, the first ionization energy, you use the neutral atom. The second ionization energy, you use the +1 cation. So here, this is electron affinity 1. If you want the electron affinity 2, then you use the product on the first reaction. The product on the first reaction is the -1 anion. So the second electron affinity would be, you start with your anion in the gas phase. This anion gets an additional electron, and you obtain a -2 anion. And then from here, well, you keep going pretty much the same way. So you will start adding electrons to the next anion in the count. So how the ionization and the electron affinity changes as you move through the periodic table? Well, this is a little more complicated because there are different tendencies here. There are atoms that will want to gain the electron, and there are atoms that they don't want to gain the electron. And that pretty much means that because those atoms will like to get the electron, they gain stability. So remember, for example, the halogens. And the one thing to remember is everyone wants to be like the Nobel gas, right? Halogens will do that by gaining 1 electron. So they really want it because it gives it, getting that electron gives them a lot of stability. But in the case of a group 1 metal, well, if you think in terms of lithium to acquire a noble gas configuration by gaining electrons, it has to gain 7 electrons. So it's more difficult for lithium to gain 7 electrons than it is to lose 1 electron and then get the configuration of helium. So it's much easier for lithium to do that. So therefore lithium doesn't really want to gain that electron. Okay? So that's the basic concept here. So, but if you were to predict what's happening with electron affinity, so there is an increasing tendency to gain the electrons on the right side of the periodic table. So this side of the periodic table, and remember what's in that side of the periodic table, that's the nonmetals. So these tend to gain electrons. Now what happens on the left side of the periodic table? You have metals on that side. They don't want to gain electrons, they want to lose electrons. So there is more tendency to lose electrons on this side. Okay, so more likely you will see electron affinities with positive values on this side, and you will see electron affinities with negative values on the other side. So let's write it down. Negative. Generally speaking, on this side you will see positive values. It's not much stability that they gain, and sometimes they will actually, you have to provide energy for that atom to accept the electron. So that's why you see larger negative values for halogen and less negative, or in some cases even positive values for metals compared to the non-metals. So that's what happens with electron affinity. So these are the values that you see here. Once again, the halogens, okay, large negative values. Always remember that. Those are the largest values of electron affinity. They really want that electron, okay? Now, an interesting case happened with group 1 and 2 metals, and the one thing that you have to remember is that for these metals, group 1, the last electron, the configuration is S1, and in group 2 you have S2. Okay, and the impact that that has is that, for example, for the alkali metals, let's say for an alkali metal you have the 1s, the ns orbital, and you only have one electron there. Okay, so adding another electron, it goes in the same orbital. Okay, you gain stability. You are still pairing those two electrons. You are kind of, for those, well, you are filling up that orbital, gives certain stability. But with the ns, if you are to put another electron there, then the ns orbital is already full, so you have to go to the np orbital. So that electron cannot go there, but has to go in this. And the np orbital is higher in energy, so you need to provide the energy for that to happen. So that's the main thing. That's why you see a negative value in group 1. Okay, negative electron affinity in group 1, but positive in group 2. Okay, so group 1, the electron goes in the s orbital. Group 2, the electron has to go in the p orbital because there is no space in the s orbital, and that requires energy. Okay, when you go to the other side of the periodic table in the p block, remember this is s block. When you are in the p block, then all those orbitals, all those p orbitals, there is always room all the way to the halogens. You still have room for those to put electrons on those orbitals. And you see, generally speaking, negative values here because adding electrons to that p orbital is start taking you closer and closer to the noble gas configuration. So anyway, you are gaining some stability there. That's why you see the negative values there. Okay, so the thing to remember here is that if you are putting electrons in a higher energy orbitals, generally speaking, you will require more energy for that to happen. Okay, so what is important to notice? This is the key to understand why the elements behave the way they do. And with electron affinity and ionization energy, well, you can pretty much, having two elements, you can predict, okay, what's going to happen if you combine these two numbers, these two elements. Okay, so in the simplest way, we can explain this based on, first, the ionization energy tells you how much that atom is attracting its own electrons, how much that atom wants to retain its own electrons. So the non-metals have a high ionization energy, so they don't want to lose electrons. Okay, they want to gain electrons, and you see that because now you take a look at the electron affinity, and that tells you about how much that atom is attracting other electrons. Okay, not its own electrons, but electrons coming from a different source. So if you have a higher negative electron affinity, then it means you will have a higher ionization energies because you don't want to lose your own electrons, but you want to gain electrons from other ways, from other sources. Okay, the metals have low ionization energies, and non-metals has high ionization energies. Okay, metals want to lose electrons, non-metals don't want to lose electrons, they want to gain electrons. Okay, so, and that has an impact on the properties of metals and non-metals. And just to remember, what are some of the properties of metals? They are malleable and ductile. This means you can make shapes out of metals, and ductile means you can make wires out of them. And metals, generally speaking, is shiny, lustrous, but probably the main thing you can relate with metals is this: malleable and ductile. They are good conductors of heat and electricity, and probably in terms of chemistry, the most important for you to know is that they tend to form cations, and they form cations by losing electrons. So generally speaking, metals gets oxidized. Okay, oxidized meaning they tend to lose electrons. Now, on the other hand, non-metals are practically the opposite. If you can make shapes out of metals, well, that doesn't happen with non-metals. They are brittle, so let's say, meaning they are uh, easily break down. Okay, they are not shiny, non-reflective, totally the opposite. Electrical and thermal insulators, that means not good conductors of heat and electricity, so the opposite of the metals. And probably the most important thing in terms of chemistry that we need to remember is that the non-metals tend to form anions and polyatomic anions, and they do that by gaining electrons, so they get reduced. So those are kind of the main difference between metals and non-metals. And now we want to explain why that happens in terms of, particularly for the metals. So the metallic character refers to how close a given element is to the ideal metal. And what's an ideal metal? Well, an ideal metal is the main properties that we were discussing: more malleable, easier to make shapes out of it, more ductile, easier to make wires out of it, better conductors of electricity. So, well, that talks by itself, right? But here, again, from the point of view of chemistry, they are easier to ionize. And easier to ionize, in this case, means easier to lose electrons. That's what a metal will do. Is if they are ionized, it means they are losing an electron, because that's what metals want to do. Okay. So now, if we take a look at the periodic table, again, this is about how that character changes with the periodic table. So it's a metallic character. So we are trying to locate the best metal. Now, what you see here is that it decreases. Let's call MC metallic character. If you go left to right, it decreases. Left to right. So, in other words, if you go left to right, you are going farther and farther away from the ideal metal. Now, when you go down the group, then the metallic character increases. Okay, and the metallic character increases, meaning that metal down the group, it's easier to make shapes out of it, makes easier to make wires, and it's easier to ionize. So in that regard, pretty much, if you look here at francium, that is going to be your perfect metal. Okay, so if the metallic character is decreasing left to right, well, it's increasing in the other direction, right? So that corner right there with the francium would be your perfect metal. Okay, things to remember here, and remember, part of the metallic character is the tendency to lose electrons. So if you go down the group, your ionization energy decreases. If you go left to right, your ionization energy increases, and then the relationship here should be clear, right? If the ionization energy increases, then you are going farther away from the perfect metal, because the perfect metal should be easy to ionize, and it won't be easy to ionize if you have a high ionization energy. And in this case, down the group, the ionization energy is decreasing, so it's easier to remove those electrons, it's easier to ionize that metal, and that's why the metallic character increases. So that's what all there is to this. Okay, metals always have smaller ionization energy compared to non-metals. And remember, the metallic character increases down the column because of the size. Those electrons are farther away. Okay, size increases, then easier to remove electrons, and that's why the metallic character increases. Okay, and same thing here, metallic character decrease across the period because the electrons are held more strongly. The atom is smaller, it's more difficult to remove the electrons. Okay, so basically that's it in terms of periodic properties, and we'll be discussing this in class next time.